Assalamualaikum. Hi everyone. So this is a video for chapter 2, Thermochemistry. So for today's lesson, for 2.1 concept of enthalpy, at the end of this lesson, you should be able to first explain about endothermic and exothermic reaction using the complete energy profile diagram, and then state standard conditions of reaction and define the following terms, which is enthalpy and also standard enthalpy. And lastly, define and write thermochemical equation for each enthalpy below. So we have 6 different enthalpies here: enthalpy of formation, combustion, atomization, neutralization, hydration, solution or dissolution. So let's start. When going into chapter 2, thermodynamics, we need to know the important terms inside thermodynamic. Okay. So what are the important terms for thermochemistry? Okay, so these are some important terms. So the first one that we're going to look on is the definition of thermochemistry itself. So what is thermochemistry? So basically it's a study of heat change in chemical process. So from the word itself, the word thermo here means heat. Okay, and chemistry is what we are studying right now. Okay, so we are studying about the heat change in a reaction. Okay. Next, we have heat and heat flow. So, what does heat and what is heat flow? So, by definition, heat is energy transferred between two bodies of different temperature. Heat is a type of energy. Okay. So, you need to be able to differentiate between here what is heat and what is temperature. It looks like it's the same thing, okay, but heat and temperature is two different things only on the same subject matter. Okay, what do I mean by that? Like I said, heat is a type of energy and temperature is used to observe the heat change. Okay, because for temperature, what do you understand about temperature? You know, we have degrees Celsius, Kelvin, and some use Fahrenheit. Okay, it's a measurement, it's a value to show either the heat increase or decrease. Okay, so that is temperature. So do you get the difference between heat and temperature? Now, the next part, we have here heat flow. Okay, for heat flow, it's energy transferred. So when we talk about energy transfer, it will always be from a hotter body to a colder one. Heat will flow from higher temperature to lower temperature, and it will always be like that. Okay, so the next thing, when we talk about thermochemistry, we need to understand these two terms. Okay, the next two terms are system and surrounding. What is system? It's any specific part of the universe that we wish to observe on its changes. So to make it simpler, what is our system actually? It's our reaction. And everything besides that, everything besides the reaction, we call it as the surrounding. So everything that lies outside the system. So to make it simple, for the system and surrounding, so let's say I have a beaker, okay, where inside this beaker I put HCl and NaOH. So I have a solution inside here, so HCl and NaOH will undergo a neutralization reaction. So this is my system. Okay, when this reaction occurs, it will produce heat. So this heat will be absorbed by something else, meaning it will be absorbed to the surrounding. So what are my surroundings? So basically everything besides then the reaction itself. Beside then the reaction inside here. The beaker itself, the glass beaker itself is also the surrounding. Why? Because glass can absorb heat that produced from the reaction. Okay, this one we will talk about it later. Okay, now the next thing we're going to look is about system. So to talk about system, we have here 3 different types of system. So what system do we have? First, we have an open system. So open system is system that can exchange mass and energy with its surrounding. Okay, let's take a look on the 3 terms first. And then we have closed system, system that allows exchange of energy with its surrounding, and isolated system, system that does not allow the change of either mass or energy with its surrounding. Okay, so how do we differentiate between these 3 systems? So now let's take a look. So these are our 3 systems just now, our open system, closed system, and isolated system. And I highlighted here what's the difference between the 3 systems. Okay, so let me explain one by one by simple drawings. Okay, so when we talk about open system, so for example, you do a chemical reaction. Okay, so chemical reaction, I put in NaOH plus HCl. So I do a neutralization reaction. Okay, when I have an open system, what does it mean? So I just do the reaction just like this, meaning inside the beaker, and then I just pour in the solution and the reaction will occur. Meaning there will be chances of energy released to the surrounding, heat is absorbed to the surrounding, and also maybe some of the solution here is splattered outside or transferred outside. Okay, or maybe the solution might evaporated. So this is an example of open system where we can exchange mass and also energy. Now, so this is open system. Okay, next I want to talk about a closed system. Okay, I'm doing the same reaction. Okay, I'm still adding inside my beaker here NaOH and also HCl. But the difference here is I do the reaction and then I close the beaker. I close the beaker with a lid over here. So this is what we call as a closed system, where there might be some transfer of heat from the reaction, from the system here to the surrounding outside. Okay, but there will be no exchange of mass. The mass cannot be transferred out. Why? Because I closed the system already. I closed the beaker with a lid. So there should be no loss of mass. So this is a closed system. Next, we want to talk about isolated system. So isolated system, it says here, does not allow the exchange of either mass or energy. Okay, how will the reaction occur? Same reaction. Okay, I have my beaker and then I put a lid, and at the same time I put an insulator. Okay, insulator. So let's say I put here styrofoam. Add as insulator. So what does insulator does? It prevents the heat from escaping the reaction. So my reaction is still the same. Inside this beaker, I add sodium hydroxide with HCl. So these two reactants will react with each other. So there will be release of heat, but the heat is trapped inside the beaker. Why? Because I put an insulator here. So the heat cannot escape outside. So this is what we call as an isolated system. So make sure you can differentiate between these 3 systems. Okay, so now let's move forward. The next part, we're going to look on the types of chemical reaction. So for this one, we actually have done it previously in chapter 1. We already discussed about it. So this will be like a refreshment for you, okay, to refresh your memory. So refresh back, we have two types of chemical reaction. We have exothermic and also endothermic reaction. So we're going to look first on the exothermic reaction. So exothermic reaction is a process that releases energy from the system to the surrounding. Okay, results in a decrease in enthalpy of a system. So here we have a new term, enthalpy. So what is enthalpy? So before this, you met this H in your thermochemical equation where we put it as delta H. Okay, so later, a bit later, we're going to look what is actually enthalpy. Okay, now, so let's proceed. So the next part, the enthalpy of the reactants is greater than the enthalpy of the product. So H reactant is bigger than H product, and the delta H will equals to negative. You will get a negative value for exothermic reaction. Okay. So this is the energy profile diagram for the exothermic reaction. So like we said before, exothermic reaction is a reaction that release energy. So before this, I just mentioned it as reaction that release energy. Where does the energy goes? From where to where? So from the system to the surrounding. So this is an example of a thermochemical equation. How do we know that this equation, this reaction, is an exothermic reaction? By looking at the value of the delta H. So when you have a negative value, meaning we have an exothermic reaction. And to draw the energy level diagram here, energy profile diagram, pardon me, we will start with the reactants having a higher energy compared to the product. Okay, so what happened here actually? So when the reactants, 2 mole of H2 and 1 mole of oxygen reacts with each other, H2 react with O2, what happened? They will release energy during the reaction. Okay, when they release the energy, so that's why when we talk about energy, so it's directly proportional to its enthalpy. So it has higher enthalpy here. When reaction occurs, they release that energy, so that's why the product over here will have less energy. So total energy of product is less than total energy of reactant because it's already been released here. So this result in decrease in the enthalpy of the system. So the decrease here shows in the value of delta H, where we have the value as negative value. Okay, and then your energy profile diagram is still the same, where we have our reactant, products, and then our activated complex up here, the activation energy, and also the delta H reaction. Okay, now let's move forward. Next, we're going to look on endothermic reaction. So what is endothermic reaction? So it's a process that absorbs heat from the surrounding to the system. So before this, I just mentioned to you, endothermic reaction is a reaction that absorbs energy. So this is the detailed explanation. It absorbs energy from the surrounding to the system. Okay, this will result in increase of enthalpy of the system. Enthalpy of product is greater than enthalpy of the reactant. So H product is greater than H reactant. So this one will be shown on the energy profile diagram. And the delta H, the difference in enthalpy, will give us a positive value. Now, endothermic reaction. So before, I just told you that endothermic reaction is a reaction that absorbs energy. Okay, when we say that it absorbs energy, what can be used, how can we use this information to start drawing our energy profile diagram? Okay, this means that our reactant here, okay, it needs to absorb energy during the reaction process. So by the mean of it absorbing energy, meaning our reactant has lower energy initially. So it absorbs energy to do the reaction, and what happened? After the reactant absorbs energy and form product, so the product here will have higher energy. Okay, so that's why the total energy of product is more than the total energy of reactant, and that is why from the previous from the previous slide, I told you that the enthalpy of the product is higher than enthalpy of the reactant. Okay, again, because enthalpy is directly proportional to the energy. Okay, so that's why you put your reactant down here and your product up here, because the reactant needs to absorb energy. Once it absorbs energy, the product will have higher energy compared to the reactant. Okay, so that's why you draw your energy profile diagram like this. Okay, due to that, it will result in increase of the enthalpy of the system. So that's why we will get our value of delta H as positive. Okay, so this is from your energy profile diagram. This is your energy profile diagram for endothermic reaction based on this thermochemical equation. How do we know that from this equation it is an endothermic reaction? By looking at the value of delta H. So if it's positive, meaning it's an endothermic reaction. Okay, good job so far on refreshing your memory on exothermic reaction and also endothermic reaction. So in the previous slide, I mentioned about enthalpy. So what is actually enthalpy? Now we're going to look on the concept of enthalpy. So for concept of enthalpy, the first thing, what is enthalpy? So enthalpy is the amount of heat flow in or out of a system. Okay, so now you have three different terms that correspond to almost similar thing. Okay, we have heat, temperature, and now we have enthalpy. All correspond to similar thing, all talks about similar thing, but it's actually different. So let me refresh your memory. Heat is energy, it's a type of energy transferred. Temperature is a measurement of the heat, so that we can know what is the temperature in degrees Celsius. Is a measurable unit. And then enthalpy is amount of heat flow. Heat itself is only an energy, but enthalpy is heat flow, okay, in or out of a system. So for enthalpy, we have two different types of enthalpy. First, we have enthalpy change, delta H. Okay, so this is the difference between the enthalpies of the product and the enthalpies of reactant. We can also write it down like this. So delta H, delta H reaction equals to delta H of product minus delta H of reaction. So this is for calculating our enthalpy change. And then we have another term. Oh, okay, so I have it here actually. So let me erase this for you. Okay, delta H is delta H of product minus H of reactants. Okay, the next one we have standard enthalpy change. So please make sure, look closely on the unit here. Not the unit, the symbol. Enthalpy change is only delta H, but for standard enthalpy change, you have delta H naught over here. So what's the difference between these two? Okay, so the difference is, for standard enthalpy change, it's enthalpy change for a certain reaction at standard condition. So actually it's the same thing. Okay, enthalpy is still an enthalpy change, but when we talk about standard, meaning we have our standard condition. So what are our standard condition? It will be the temperature of 298 Kelvin or 25 degrees Celsius and 1 atm pressure. Okay, so other than this temperature and this pressure, if we do a reaction besides 25 degrees Celsius and 1 atm pressure, what we will calculate is only the enthalpy change. But if we did the reaction at 25 degrees Celsius and 1 atm pressure, we will have a standard enthalpy change. Okay? Next, the two important aspects of delta H that you need to know. The first one is sign. Okay, positive or negative. So if you look here, the first equation, I have 2H2O to produce 2H2 plus O2 with the delta H positive 572 kilojoule. So it's an endothermic reaction. So if I reverse this reaction, okay, I reverse this reaction, meaning I will get a chemical equation as 2H2 plus O2 to produce 2H2O without changing the numbers here. So the value of the delta H, the numbers is the same, but what happened now is the sign will change. It will become negative. Okay, so this is the first one, the sign. Okay, the second one is magnitude. So magnitude is basically based on its stoichiometric relationship. So what does this mean? So for example here, I have 2H2 plus O2 to produce 2H2O liquid. So I have delta H is negative 572 kilojoule. Okay. If I want to remove the number 2 here, so I need to divide all the equation here by 2. So I have H2 plus half O2 to produce H2O. So if I divide everything here by 2, my delta H also must be divided by 2. So that's why you will get the value here. Okay, the delta H is half the initial value. So please take note about these two aspects of delta H. It will be useful later when we start on our 2.3. Okay, so take note of this. So now we're going to look on different enthalpy of reaction. So the reaction here, we're going to focus on specific reaction such as formation, solution, combustion, neutralization, hydration, and atomization. For this different enthalpy of reaction, the way of writing down the thermochemical equation is based on the definition of the reaction itself. So you need to make sure that you memorize correctly all the different enthalpies. So refer to your note. Let's take a look on what are the enthalpy that we have. Okay, so this is the same as your notes where we have here 6 different enthalpy, and I already divide the enthalpy so that it will be easy for you to memorize them. Okay, you need to make sure when stating the definition of enthalpy, first you need to have the name and then the heat. Okay, either it is heat change, heat release, or heat absorb. So this must be very specific because from the heat itself, from the heat change, either release or absorb, it will be shown on the thermochemical equation. Okay, and to write down the thermochemical equation, the value here, the value of the delta H here, it will depends on 1 mole of something. So you have here per mole. So that 1 mole must refer to either the reactant or the product. It cannot be both. Okay, how do we determine either it is the 1 mole is for the reactant or for the product or for specific species in the reaction? That will be based on the definition itself. Okay, so what do I mean by this? So let's take a look one by one on the definition. So the first one here, we have enthalpy of formation. Okay, enthalpy of formation, delta H node F. Okay, for formation, it will always be delta H node here. Okay, and then small f down here. Make sure you know how to write the symbol correctly. It's delta H node F, like that. Okay, why must formation have node? Okay, because if you look at the definition, enthalpy of formation is heat change. So when I said heat change, it can either be both. It can be released or it can be absorbed. Okay, heat change when 1 mole of compound is formed. Okay, 1 mole of compound is formed from its element in their stable state at standard condition. So I repeat, for enthalpy of formation, heat change when 1 mole of compound is formed from its elements in their stable state at standard condition. So what does this mean? Okay, so this means when I want to write down the thermochemical equation, I want to write down the equation. Okay, the 1 mole must refer to the compound form. So from this equation, the one that I want to form is H2O. So you need to make sure that H2O is 1 mole. Okay, and then H2O is formed from its element. So what is the element of H2O? So the element of H2O is hydrogen and oxygen. Okay, so it will be hydrogen and oxygen from its stable state. Okay, what is the most stable state? For hydrogen is H2 gas and oxygen is O2 gas. So balance your equation. Okay, so let's take a look on the side. So just now I give you H2. Okay, it will be like this. Our 1 mole that we want to form is H2O. So H2O is formed from its element, which is hydrogen and oxygen. Okay, at standard condition, hydrogen exists as H2 gas. So this is the most stable state of hydrogen. And then for oxygen is O2 gas. Okay, so let's say H2O here, you have it as liquid. Okay, you need to balance this equation. So to balance this equation, usually what you will do is you will put either you put half H2 here. Sorry, you cannot put half H2 here. Okay, usually what you will do is you put the number of 2 here and then you put 2 H2 over here. Okay, so you have 4 H2 plus O2 to produce 2 H2O. Okay, correct? But if you write it like this does not represent the enthalpy of formation. Okay, like I said before, for enthalpy of formation, we need to make sure that this is 1 mole. Okay, so the correct equation will be H2 gas plus half O2 gas to produce H2O. So like I said, from the definition, it's 1 mole of compound form. So this is the compound form. So you need to make sure that H2O is 1 mole. So, the second one is enthalpy of solution, or also known as enthalpy of dissolution. The symbol for enthalpy of solution is delta H solution. The definition for enthalpy of solution is heat change. Okay, it can either be heat release or heat absorb. Okay, it's not specifically release or only absorb. Okay, heat change when 1 mole of substance dissolve in solvent to form an infinite dilute solution. So, it's talk about here, the 1 mole is for the substance dissolved. Okay, so you need to focus, the 1 mole is the substance. So, our substance here is our reactant, okay, KCl, and it must be solid because it is dissolved in solvent. Okay, it's either solid or liquid. Okay, but usually it will only be solid. Okay, for enthalpy of solution, we want to make a solution from a solid compound, and that solid compound need to be 1 mole. Okay, so the focus of 1 mole is there, and the delta H solution will be written as this. It can either be positive value or negative value, depends on the type of substance that we have. Okay, now the next one, we're going to look enthalpy of combustion. So for enthalpy of combustion, okay, combustion over here, enthalpy of combustion, delta HCOMB, it will always be heat release. Combustion must release heat. So the definition of enthalpy of combustion is heat release when 1 mole of substance completely combusted in oxygen. Or you can also write completely burn. Okay, completely burn in excess oxygen, as the definition of delta H combustion, enthalpy of combustion. Okay, so with that being said, since it said that 1 mole of substance, here, substance, 1 mole, completely combusted, meaning you need to make sure that here, the substance over here must be 1 mole. Okay, so for example, I show you how to write down the equation for this one. So, for that equation, CH3OH plus O2 to produce CO2 plus H2O. So, let's say this is your equation, and please, you need to make sure that for chapter 2, all your reactions must have phase. Okay, so gas, carbon dioxide is also gas, H2O over here is liquid. Okay, so by right, if you balance this equation, what you will do is you will get the balance equation as 2CH3OH plus 3O2 and then 2 carbon dioxide with 4 H2O. Normally, you will balance it like this. Okay, but this balance equation is not comply for delta H combustion. Okay, the equation is not correct for delta H combustion. It is wrong. Why? If you look back at the definition says that 1 mole of compound, so we need to make sure that this substance must be 1 mole for it to be delta H combustion. So that's why we divide everything by 2. So the correct equation to show for delta H combustion is CH3OH OH plus 3/2 oxygen gas to produce 1 CO2 gas plus 2 H2O liquid. Okay, so this one, the one that I write in purple color over here, this is the correct delta H equation for delta H combustion. The one that I write just now, it is not correct because it is not 1 mole. The substance is not 1 mole. So please remember your chemical equation based on definition. Check which substance needs to be 1 mole. Okay, the next one, after delta H combustion, we're going to look on the enthalpy of neutralization, delta H neutralization. So the definition of delta H neutralization is heat release, okay, when 1 mole of water is formed when acid reacts completely with base. So your focus over here, your 1 mole is for the water molecule form. So you need to make sure that H2O here must be 1 mole. The value of delta H here refer to when 1 mole of water is formed. Okay, and you must have a balanced equation over here between acid and base. The definition, it must have when acid reacts completely with base. Meaning when the question asks for definition, you must give everything that you see here. Okay, enthalpy of neutralization, heat release when 1 mole of water is formed when acid reacts completely with base. And then when the question asks, write down the thermochemical equation. So please bear in mind when the question asks for thermochemical equation, it's the complete balanced equation with the delta H. You must put the delta H. If you just write down the balanced chemical equation only, this is not considered as thermochemical equation because thermochemical equation must have the information on the enthalpy of the reaction. Okay, so that's that one is for enthalpy of neutralization. Okay, the next one that are still in terms of heat release is we have enthalpy of hydration. So enthalpy of hydration is heat release when 1 mole of gaseous ion is hydrated in aqueous solution. Okay, so your 1 mole here must refer to a gaseous ion, and this gaseous ion must be 1 mole. Okay, 1 only. So for example is Na plus, and the phase must be in gas phase. Okay, compulsory to be in gas phase over here, and then it will produce still an ion Na plus, but the phase will change, it will become aqueous. Okay, so meaning the energy here, the energy released, the negative 406 kilojoule per mole release here is due to hydration of 1 mole of Na plus gas ion. So the last one here we have enthalpy of atomization, so delta H atom. So for atomization, it will always be heat absorbed when 1 mole of gaseous atom is formed from its element. It must be from its element. Okay, so element first, the 1 mole. So we need to make sure that 1 mole of gaseous atom form. So it must be our product over here. Okay, we need to focus on the formation of 1 mole of gaseous atom, and it must be formed from its element, and this element must be the most stable form. Okay, so what do I mean by here? So example here, sodium. We want to form 1 mole of sodium gas. So the most stable state sodium element is Na solid. It's not Na liquid, not Na gas, but it must be Na solid. So same goes with Cl. Okay, its element is Cl2. Okay, the most stable state for chlorine is chlorine gas. So that's why you have here Cl2 gas. Since we want only 1 mole of gas, chlorine gas over here, so that's why on the left hand side, it's half Cl2. So that I can have 1 Cl atom only. Okay, so please make sure when we talk about element, just one element only. Okay, what do I mean by this? So let's say I want to write down the enthalpy formation of oxygen. Okay, oxygen gas. So can I take it from H2O? Okay, so is this equation correct? This is wrong. Why? This is because the element for oxygen or gas here, it must be only oxygen. So here I have two different elements. I have hydrogen, I have oxygen. So that's why this is wrong. Okay, for me to write down the atomization of oxygen atom, it must be from an oxygen gas. So only one element here. And the most stable state for oxygen is gas. So since I need to balance the right hand side, I have 1 mole. Here I have only 1 oxygen. Here I have 2. So that's why times by half. So left hand side I have 1 over 2 times 2 equals to 1. So 1 oxygen. Product also 1 oxygen. Okay, so I hope it is clear for you. Now, the next part, if you look at my table, okay, I separate enthalpy and standard enthalpy. Okay, except for enthalpy of formation. So for enthalpy of formation, it must be the definition, heat change when 1 mole of compound formed from its element in their stable state at standard condition 1 atm and 298 Kelvin. This bracket must be stated as well. Okay, but for the other enthalpies, if the question just asks about enthalpy, okay, this will be your definition. But if let's say it asks for standard enthalpy, for example, give the definition of standard enthalpy of atomization. So how are you going to state the definition? It will be heat absorbed when 1 mole of gaseous atom is formed from its element at standard condition of 1 atm and 298 Kelvin. Or if you don't want to write in Kelvin, you can write the temperature in degrees Celsius, which is 25 degrees Celsius. So that's the difference. And then the other difference is the symbol. So if let's say you want to write down standard enthalpy formation of atomization, so it will be delta H naught atom. Okay, so I hope you are clear about this, and please make sure this is compulsory. You need to memorize all these 6 enthalpy by heart. Okay, memorize each word. Okay, because this is very, very, very important later for us to look for 2.3 and also 2.4. Okay guys, so please make sure that you memorize all the definitions that we have discussed just now, because it is very, very, very important. So until we meet again in the next video. Thank you.